Okay, this is Regents Chemistry Review by Example. So what that means is we're actually going to be working through some different types of questions while we're reviewing. So a couple of things that you need handy are your reference tables, something to write with, a calculator, some scrap paper, and more importantly, you need to be able to pause me and try to think about the questions, because I'm just going to be going through them all. You should actually pause, try to do a few, and make sure that you're coming up with the same answers. Now, I'm not going to get to nuclear today, even though it does say nuclear. We're going to talk about matter and energy. Probably won't even get into any atomic structure today. I don't want to make the lesson too long, but in this first session, so it's probably going to be 1A. Well, this is like 1A, and there'll be 1B. The smaller the sessions, the easier it is for you to stay focused and I can keep your attention. So let's get started. The first thing you're going to need is Table S. Please don't forget about Table S. It has a lot of useful information on it. Not only does it give you the names and the chemical symbols, it gives you the melting point, the boiling point, it gives you the atomic radius, electronegativity value, ionization energy, and really important is density, because they always throw a density question in and it's not something that we really talk about. The density for all the elements are listed there. So when we go to Table S, we want to be able to look up silver, and we should be able to write that it's Ag. We should be able to look up cadmium, and we should be able to write Cd. Tin is the weird one. It doesn't sound anything like its name. It's Sn. Au is gold, so now we're going to write the name. Hg is mercury. Rn is radon. Ra is radium. Oh, we have a repeat, so we have mercury again. And Br is bromine. So while I'm here and I have bromine and mercury listed, I want you to realize that these two elements are the only two elements that are liquids at STP. So at standard temperature and pressure, these are the only two elements on the entire periodic table that are liquids at STP. In this next section, they want us to label element, compound, or mixture. They want us to state whether it's homogeneous or heterogeneous, and whether it's pure or impure for each substance. So let's just do a little review right here in the middle. First of all, everything is made up of matter. And matter can be a pure substance, or it can be a mixture. And under pure substance, we only have two types. We have elements, and then we have compounds. And what do we know about elements? They can't be broken down. They are in their simplest state. And what we know about compounds is that they can be broken down by chemical means. Because if they're a compound, they were put together by chemical means. Therefore, they can only be taken apart by chemical means. Now, over here under mixture, we have two types. We have homogeneous, and we have heterogeneous. And mixtures can be separated. So one note is that they can be separated, and that would be by physical means. And what I mean by physical means, there are a couple of things, and we'll talk about these in a different lesson. But you have distillation, which is separation by boiling point. You have filtration, so that's based on particle size. And you have evaporation, where you can evaporate all the liquid and be left with a solid. We also have chromatography, which has to do with a separation of a mixture based on polarity and size. So we have homogeneous and heterogeneous. Homogeneous means it's consistent throughout. So solutions, all solutions are homogeneous. Because if I dissolve salt in water and I stir it and it all dissolves, it's consistent throughout. It all looks the same. Heterogeneous is not consistent throughout, and some examples here could be, like an example here could be Italian dressing. So you have the vinegar, oil, and spices, and if you shake it up, it's not consistent throughout. It'll separate. Another good one is chocolate chip cookie dough. You can't be assured that you're going to get the same number of chips in each spoon of dough, so it's not evenly distributed. Those are all good ones. So now that we have some understanding of that, let's go back and look at what we have. So we have NaCl, solid, liquid, and gas. Well, first of all, we know NaCl is a compound, and we know that compounds are pure, and we know that they're homogeneous. They're consistent throughout. So if I have water, H2O, it's a compound, it's consistent throughout. NaCl aqueous is a mixture because it's aqueous, and it's homogeneous because it is a solution, and all solutions are homogeneous, and it is impure because it is mixed with water. The only things that are pure are elements and compounds. The only things that are pure, see pure substance, are elements and compounds. And our last one over here, NaCl mixed in a bag with sand. I'm going to put that down below. So we know that this is also a mixture. And this is going to be heterogeneous because we can't be assured that the NaCl is going to be evenly distributed throughout the bag of sand. So this is going to be heterogeneous. And it is impure. Okay. Another important thing that we need to know is particle diagrams. These are called particle diagrams, and the Regents loves these, and you need to know how to draw them and interpret them. So before we even talk about these particle diagrams, let's talk about some simple things. So first of all, a compound is two or more different things chemically combined. So if I were to draw a compound as a particle diagram, this could be a compound because I have two or more different things bonded together. Maybe I have something that looks like this. So this could also be a compound. So these are examples of compounds. Two or more different things chemically combined. When we talk about elements, we have an element could just be a hollow circle, or it could be drawn as a solid sphere. This would be considered a monatomic element, meaning only one. And then you also know that we have something called diatomic elements, and that's your Brinkelhoff. So we have diatomic elements, or diatomic molecules. So diatomic molecules, because in nature they are found bonded to one another. And underneath here, I'm just going to put BRINCLHOF, Brinkelhoff. Those are the 7 diatomic molecules. Okay, so let's look at what we have going on here. They want us to determine whether we have elements, compounds, or mixtures. So in the first box, we can see that we have a compound, and it's the same kind. So it's basically one compound. Here I see a compound, and then I see a different type of compound. So this is a mixture. And if I want to be specific, I could say it's a mixture of compounds. Over here, I've got a compound, two different things, and then I have diatomic molecules. So this is also a mixture. If I want to be specific, it's a mixture of diatomic molecules and a compound. Over here I have a mixture, and if I want to be specific, it is a mixture of monatomic and diatomic molecules, or elements, diatomic. Over here I have a mixture of monatomic elements. And in the last one I have diatomic molecules, and these actually look like they are in the solid phase, where everything else kind of looks like it's in the gas phase. Okay, going with what we just did, we need to determine if the following substances are elements, compounds, pure substances, and mixtures. And we are going to check all that apply. So NaCl we know is a compound, and it's solid, so we know it's a pure substance. H2O liquid is a compound, and it is also a pure substance. NaCl aqueous, it is a mixture, and it is, well, I guess it's a compound, but it's mixed with water, so there's two compounds. This is kind of iffy here. I'd say it would be a mixture of compounds, so it's plural. So you've got the NaCl and you have H2O. Mercury nitrate, that is aqueous, so that's also going to be a mixture. And again, we could say that there's two compounds here. One is the HgNO3 and the other is the water. Nitrogen gas is an element. It is a pure substance. Magnesium solid is an element and also a pure substance. And then H2SO4 liquid. This is a compound and it's pure. So the only thing I'm questioning, it depends on how the question is written here. Either they just be left as mixtures, or you could say it was a mixture of compounds because you have both NaCl and H2O in there. What's the difference between a chemical change and a physical change? Well, physical change is simply a change of state. I take water, I put it in the freezer, it turns solid. I take it out, it melted, it turns back to liquid. I take the glass of water, put it out in the sun, and it evaporates. Physical change. I can get back what I started with. Chemical change, I can't get back what I started with. I take a piece of paper, I rip them up in tiny pieces. That's a physical change. As soon as I light them on fire and they burn and all I have left is carbon ash, that is now a chemical change. When I take a nail and I leave it outside and it rains and it snows and it sleets and after time it rusts, that's oxidation. It's a chemical change. So salt dissolving in water, that would be physical. I can get my salt back by evaporating the water. Melting of iron is physical. Cool it down, I get back the solid. Burning of wood, definitely chemical. I can't get back my log. and a liquid turns into a gas? Well, if it's in a closed container, then I can get it back. That would be physical. Hopefully it's done in a closed container. Tips for determining exothermic and endothermic reactions. Think of a chemical reaction, the actual equation, as a two-room building, which has an arrow that denotes where the exit door is. So there's the exit sign, and it's pointing right. Now that we know where the exit door is, let's label the exit and entrance. So the left side would be the entrance. Notice EN is underlined. And the right side would be the exit. Notice EX is underlined. Let's ask ourselves, in which room does the heat reside? The room with the entrance or the exit. So here, heat is on the right. It's in the room with the exit. So this is going to be exothermic. When we look at this equation, where does heat reside? Sorry. Okay, they take more steps to get to where I already got. So heat is in the room with the exit, so it's exothermic. If heat was on the left, so if I had A plus B plus heat yields C plus D, then my heat resides in the room with the entrance, so this would be endothermic. And we're going to get back to that. I do a lot of layering, meaning I will briefly talk about some topics and then we're going to come back to them in a later review session. And that's kind of the way I teach all year long, is layering, because then when you actually learn it, you're like, well, didn't we learn this already? And we actually already did, but now it's just being reinforced. Let's look at this reaction and let's determine what's going on. So a couple of things that I notice. I notice that I have a double arrow, which means that the reaction can go both ways. It can go in the forward direction and produce NH3, which is ammonia, or it can go in the reverse reaction and break down ammonia into N2 and H2 gas. I notice that my heat value is in the exit room. So this is an exothermic reaction. So let's answer a bunch of questions. For the forward reaction, left to right, list the terms that can be used to describe the forward reaction. Well, first of all, left to right, heat's on the right, so we know that it's exothermic. That's one thing. Second, we can see that two items are being put together to form one. We refer to this as synthesis. Synthesis means to make. Sometimes it's called formation. And if we assign oxidation numbers to these, N2 is by itself. Anything in the free state gets assigned a 0. H2 is by itself. Again, anything in the free state gets assigned a 0. We know H is plus 1 times 3 is positive 3. It's a compound. The net charge has to be 0. So my nitrogen has to be negative 3. So I've got nitrogen going from 0 to negative 3. I'm going to put that over here. N2 0 going to N minus 3. I'm going to go ahead, and I don't need to do this here, but I'm going to take the opportunity to write a balanced half reaction. So first thing I want to do is balance my mass. I've got N2 here, so I need 2 N's here. That gives me a 2 times negative 3, which is a negative 6. So remember, I always add my electrons to the side with the higher charge. Well, 0 is greater than negative 3, so I add 6 electrons to the left. That balances this negative 6 over here. So this is my reduction reaction. Remember, Leo says GER, loss of electrons is oxidation, gain of electrons is reduction. Then I have 3H20 going to H plus 1. And I need 3 to balance. Oh, I have 3 times 2 is 6. So I need 6 H's here. These all have a plus 1 charge, so that's a positive 6 so I need to add 6 electrons. And I always add my electrons to the side with the higher charge. Plus is greater than 0. And this is my oxidation. Remember, Leo, loss of electrons is oxidation. So my oxidation number becomes more positive. I went from 0 to +1 because when we lose, we become more positive. Reduction, gain of electrons is reduction. When I gain negative charge, I become more negative. So this went from 0 to -3 because it gained electrons, which are negative. So this can also be classified as a redox reaction. If you haven't studied redox yet, then this may be new to you, and then when you do study redox, it'll help make a little bit more sense. For the reverse reaction, so if I go in the reverse reaction, so that would mean I would have 91.8 kilojoules plus 2NH3 yields H2 and N2. So now, if I rewrite this in the reverse reaction, and I really want you to see it, so I'm going to rewrite it, I've got 91.8 plus 2NH3 yields 3H2 plus N2. So notice now that my heat value is in the entrance. So this reverse reaction is endothermic, and we are breaking down the NH3, so this is decomposition, and it's still redox. It's still redox because I still have reduction and oxidation occurring simultaneously. So is the decomposition reaction endo or exit? So this is the decomp, the one we just did. We said that that's endo. The formation, remember formation is another word for synthesis. So is the synthesis reaction, that's this one, the one up top, we said that that was exo. In the decomposition reaction, is energy being absorbed? Well, here's the decomp. We said it was endo, so that means energy is being absorbed. And in the synthesis reaction, which is up here, it was exo, so energy is being released. Is the heat of formation for formation, meaning synthesis, positive or negative? Well, remember, and we're going to talk about this in a minute, in an exothermic curve, our products, so here's reactants, here's products, our products are lower than our reactants. And remember, delta H is always equal to potential energy, the products, minus potential energy, the reactants. P minus R, you can remember it well because P comes before R in the alphabet. So this number, this value for P is going to be less than R. So our delta H is going to be negative. And for decomposition, we said this is endo, so we're going uphill. Therefore, my products are going to be higher than my reactants. So this is going to have a positive delta H. In the formation reaction, which has more potential energy, reactants or products, so formation is synthesis, which we said was this one, and we can see that R is higher than P, so our reactants are going to have more potential energy than our products. But in our decomposition reaction, our products are higher than our reactants, so our products will have more potential energy. Let's figure out some math. It says, what is the enthalpy? Delta H. So they're talking about, or heat of reaction. So delta H is equal to potential energy, the products, minus the potential energy, the reactants. For the production of 1 mole and then 4 moles. Well, you can solve this two ways. You can do it straight up mathematically, or you can do it intuitively. When I look at the reaction, I see 2 moles of ammonia produce 91.8. So if I'm asking about only 1 mole of ammonia, I know it would be half of that. So I can either just divide it in half, or I can set up a proportion. So when I have 2 moles, it produces 91.8 kilojoules of energy. Therefore, if I have 1 mole, how much energy is that? So my X is going to be equal to 95.9 kilojoules. Now, Remember, this is exothermic, okay? So this is going to be released. So you either have to write the word released, or you need to put the negative sign in front of it, indicating that it's released, because it's not embedded in an equation right here. So either one of those is correct, negative 95.59 or released. Now, if I have 4 moles, you can intuitively see that 2 moles produces 91.8. So if I double that and I have 4 moles, I should be doubling my 91.8. So again, I'm starting with 2 over 91.8. And what am I going to get when I have 4 moles over x? Well, when I cross multiply and divide, I get 183.6 kilojoules. Again, it's going to be released or negative. And now they want to know how much is required for the synthesis of 0.5 moles of NH3. Same thing. I've got 2 over 91.8. This time I want to know about 0.5 moles and how much that is. And I wind up getting x equal to negative 22.95. From the previous question, what is a better word that could replace required? What's a better word that could replace required? Well, it's synthesis, so it's not really required. Energy is being released, and that's what I said. So when the synthesis takes place, this amount of energy is released in the process. Now they want to know about delta H for the decomposition of 2 moles of NH3. Well, decomposition is only going to change the sign. It's no longer going to be exothermic, but it's going to be endothermic, because that's the decomposition of NH3 right over here. So we already did that, I believe. For 2 moles, it's 91.8. However, it's going to be a positive 91.8 kilojoules, and this would be absorbed. Okay. I'm going to digress here because there are 3 things that, if you can remember, are similar, will help you on the Regents. And I call these uphill versus downhill trends. And let me take a moment to explain what I mean by that. I'm going to start with what we just used, okay? Potential energy diagrams. So, this is an endothermic curve, right? And I know that it's endothermic because I'm going uphill. And when something is endothermic, we know that energy is absorbed. And then this type of curve is exothermic. And it's going downhill. And here, energy is released. In a moment, on the next page, I'm going to talk to you in more depth about heating and cooling curves. So, a heating curve, if you recall, is like this. You have solid to liquid to gas. And anytime I go from a solid to a liquid to a gas, again, I'm going uphill, energy is absorbed. And if you think about it, what happens when you hold ice in your hand? Well, the ice melts. Why does the ice melt? Because energy is being absorbed by the ice from your hand. This is a heating curve. The opposite of that is a cooling curve. When we go from a gas, to a liquid to a solid. Here, energy is released. Notice what's happening here. I'm going uphill. Notice what's happening here. I'm going downhill. And the last thing that I want to show you is when we talk about an atom. Let's take sodium. The electron configuration 281. So here's sodium. It has 11 protons in its nucleus, and its electron configuration has 2 in the first shell, 8 in the second, and 1 in the third. When an electron jumps from a low level to a high level, so here the electron is going from low to high, it's going uphill, energy is absorbed. When that same electron, okay, so now it's 272, okay, this is called the ground state because this is what we see on the periodic table. It's the stable configuration. This would be the excited state. An electron jumps from a lower level to a higher level, leaving a lower level partially filled. When this electron goes from here back down, so the electron goes from low to high or downhill, energy is released. And that's when we see the visible spectrum. That's when we see the colored lights. I don't know if any of you did that lab in your chem class, but my students took different types of metals, lithium, and they burned it in a Bunsen burner flame, and they could see that it was magenta, and potassium was purple, and sodium was yellow, and copper, iron, well, copper was like a blue-green color. So that's as the electrons are going back down to the ground state, they release energy, and we see that visible spectrum. So here we have 3 uphill trends, and in each case, energy is being absorbed. And in the bottom, we have 3 downhill trends, and in each case, energy is being released. So this will be really helpful on the exam if you can remember the 3 uphill and downhill trends. Okay, so knowing that, let's talk about potential energy diagrams. So we know that endo is uphill, and we know that exo is downhill. Okay, they want us to label the 6 different parts of the energy diagram that you need to know. So we have 1, 2, 3, 4, 5, and then this area between the products and the reactants, 6. Okay, so 1 is, I'm going to abbreviate PE, potential energy of the reactants. Potential energy is always measured from the x-axis upward. 2 is the potential energy of the products. 3 is the potential energy of the activated complex. Remember that the activated complex is a temporary unstable state between the reactants and the products. 4 is the activation energy, written EA, activation energy of the forward reaction. So if I'm going from left to right, okay, this is the activation energy of the forward reaction, the amount of energy needed to get to the activated complex. 5 is the activation energy of the reverse reaction. So if I'm going this way, this is the amount of energy needed to get to the activated complex. And 6 is the heat of reaction, also known as delta H. And we calculate delta H, P minus R, products minus reactants, potential energy of the products minus potential energy of the reactants. So I'm also going to label those over here on this. It's the same thing. This is now 1. This is 2, 3, 4, 5, and the difference in here is 6. And remember that if we add a catalyst speeds up the rate of a reaction by creating an alternate pathway. Notice it starts where the reactant line starts and it ends where the product line is. It does not affect delta H. Do you see this? It does not affect delta H. Okay, it only affects a couple of things. There's my catalyst here. So a catalyst speeds up the rate of reaction by lowering the activation energy. So we can see now that it only takes this much energy to get to the top of the activated complex as opposed to what it was before, by lowering the activation energy. And as a side note, it also lowers the potential energy of the activated complex. And it does this by creating an alternate pathway. We are covering a lot of ground. Okay. I've got 2 more things to do, and that's going to be it. So the first thing they want us to do is label the phases of matter. So let's get right on this. Solid, liquid, gas. This is a heating curve. Right away you should know that it's going uphill, so it's going to be endothermic. They want us to label the phases of matter. So we've got solid going to liquid here, and we've got liquid going to gas up here. Then they want us to label the melting freezing point. So this is also our, I guess we would call this our MP/FP, and this would be our boiling point. Actually, it's also the condensation point if we're going downhill. Heat of fusion. So heat of fusion is here. I'm going to label that 6. Heat of vaporization happens here. This is a heating curve, as we just said. So it's endothermic. And then our heat of crystallization, or our heat of condensation, is the opposite of our heat of vaporization. So that would be if the temperature was decreasing, and our heat of crystallization is the opposite of the heat of fusion. So that would be 10. And what else did I leave out? I think we have everything else. Okay, another thing that I want to point out, I'm going to put some additional labels on here that I feel are important. I want to see if I have a color I didn't use yet. I'm going to use pink. Ooh. A, B, C. So what do we know about A, B, and C? A, B, C. That looks terrible. Okay, this is where kinetic energy is changing. Kinetic energy only changes when temperature changes. And then I guess I'm just going to label these regular. We're going to label this plateau D and E. And D and E is where potential energy is changing. So potential energy changes at the plateau where temperature is constant, and kinetic energy changes when temperature is changing. And they are directly related to the type of graph. So if we're going uphill and we're increasing temperature, then kinetic energy is increasing. If we're at a plateau, okay, potential energy is being stored, it's increasing. If it were a cooling curve, then it would be the opposite. As temperature decreases, kinetic energy would be decreasing, and at the plateaus, potential energy would be is being released. Therefore, it would be decreasing. So we have some information about this graph. They give us the time and the different temperatures, and they want to know what the melting point is. So the melting point is here. It's between 35 and 40, and if I look on my graph, I can see where I have constant data. 39, 39, 39, and that's right about this time, 4 minutes to 7 minutes, so my melting point is 39 degrees Celsius. The boiling point, again, is going to be somewhere up here between 60 and 70. As I read through my data, I can see here where data is consistent, 66 at times 11 through 14, which matches up with that, so 66 is my boiling point. We already said that it's endothermic because it's uphill. What point could represent crystallization? So we said that crystallization is the opposite of melting, number 10. So this could happen right here at 10. And under what conditions? Well, temp would have to be decreasing. So temp would have to be decreasing. Which point is heat of fusion? Heat of fusion is melting, so we said that was 6. Which point is the potential energy the most? Well, potential energy would be the most at the higher temperature, so that would be I guess we can label this E. We'll label this E. And kinetic energy would be the most when the temperature is the highest, so we can label this C. What term is used to identify the process that's taking place in this equation? This says that you're going from, it's hard to read, I2 solid directly to I2 gas. This is a buzzword that you need to know. Solid directly to gas is sublimation. It's also helpful to know that gas directly to solid is called deposition. And what other compound can undergo the same type of process, sublimation and deposition? Well, I showed you the sublimation of the iodine crystals. If you recall, that's the purple solid, and when you heat it, it turns into a purple gas, and then we cooled it back down again and we got crystals. We also talked about the other thing that does this is CO2 solid, which is dry ice, the stuff that you get when your electric goes out from the fire department. And if you leave that outside long enough, it turns directly into a vapor and a gas and disappears. Okay, this is the last section for today. This is a very long lesson. What are the two fixed points on a thermometer in Celsius and Kelvin? Well, freezing in Celsius is 0 degrees Celsius, and boiling is 100 degrees Celsius. And on the Kelvin scale, that would be 273 Kelvin and 373 Kelvin. Remember that the increments on the Celsius and the Kelvin scale are exactly the same, 1 degree. To convert from Kelvin temperature, we know from our reference tables that Kelvin equals Celsius plus 273. Here it is right here. Now, if I can take this temperature, Kelvin equals Celsius plus 273, and I want to solve for Celsius, I'm just going to do the opposite of what's here. This is addition, so this is going to be subtraction. So I'm going to subtract 273 from both sides. These cancel, so Celsius equals Kelvin minus 273. So if I want to convert 10 degrees Celsius to Kelvin, Kelvin equals Celsius. 10 plus 273 is going to be equal to 283 Kelvin. If I want to convert 220 Kelvin to Celsius, it's going to be 220 minus 273, which gives me negative 53. Negative 45 Celsius to Kelvin. So this is going to be a negative 45 plus 273, which is going to give me 228 Kelvin. This is Celsius, sorry. And 396 Kelvin to Celsius. 396 minus 273 gives me 123 Kelvin. And the last one, negative 273 Celsius to Kelvin. Well, negative 273 plus 273 would be 0 Kelvin. Okay. A liquid's freezing point is negative 38 degrees Celsius, and its boiling point is 230 Celsius. So how many Kelvin and degrees Celsius are there between them? Well, the difference between negative 38 and 230, well, negative 38 to 0 is 38 degrees, and then to 230, so that gives me 268 degrees. Now, you'll notice that I wrote this here when we're talking about Celsius. I'm going to prove to you that they're going to be exactly the same. If I were to convert these to Kelvin, negative 38 Celsius plus 273 is 235. So this is going to be 235 Kelvin. And 230 Celsius to Kelvin, so 230 plus 273 is 503 Kelvin. So the difference between 235 and 503, if I subtract these, so 503 minus 235 is 268 degrees. So as I said earlier, 1 degree on each scale is exactly the same. All right, we're going to finish up with some heat problems. Table T. The only time you use the first formula, Q equals mc delta T, is when you have a change in temperature, or you're finding either your initial or your final temperature. Q equals mH sub F. That's the mass times the heat of fusion. We use heat of fusion when we're melting, and Q equals mH sub V. H sub V is heat of vaporization. We use that when we are boiling. The hardest part about these problems is knowing how to manipulate the equation to solve for an unknown variable. So as we go through these, I'm going to mark what I've got. 20 grams, that sounds like a mass to me. So there's my mass. 20 to 60 degrees Celsius is a change in temp. So I've got a delta T equal to 40. The number of joules of heat energy absorbed. Well, remember up here, heat is Q. So Q is a question mark. We don't know what that is. So using the formula, Q equals mc delta T, because I have a change in T, I get Q equal to the mass, which is 20 grams, times C. C is the specific heat capacity of water, which they tell you that right here. But then you have to know to flip all the way to the front of your reference table to find table B and the specific heat capacity of water, 4.18 joules per gram dot Celsius. And our change in T is 40 Celsius. Notice Celsius cancel, joules cancel, oh, not joules, grams cancel. I'm left with joules, which makes sense because I'm finding Q. I multiply the three together, and I get 3344 joules, 3,344 joules. Okay, next problem. The temperature of 80 grams of water, so there's my mass. Let me change color here. Was raised to 35. So they're giving you delta T right there. Delta T is 35 by the addition of 6270 joules. So this is my Q. What was the initial temperature? So I don't know TI. Well, there's something important you have to realize, that delta T is equal to the difference between TF and TI. So if I'm looking for for TI or TF, when I'm working with the equation, I'm essentially solving for delta T. So let's see how we rearrange that equation. So we have Q equals MC delta T. I'm solving for delta T. I want this by itself. This is all multiplied, so I'm going to do the opposite, and I'm going to divide both sides by MC. These cancel. So I get delta T equals to Q divided by MC. So let me come over here. Delta T equals Q. My Q is 6270 joules divided by my mass, which is 80 grams, and my C, which is my constant, 4.18 joules per gram dot Celsius. Notice joules cancel, grams cancel. I'm left with Celsius, which is a good thing because I'm finding delta T. So 6270 divided by 80 times 4.18, and I get 18.75. That's not my answer. My delta T is equal to 18.75. Now, I added heat to the problem. I added heat. That means my temperature is going to go up. So it was raised to 35. So T35 is actually my final temperature. So if I want to know what it started at, I have to take 35 minus 18.75, and I know that it was originally at 16.25. So my TI is equal to 16.25 Celsius. Remember, I had to add heat to get to 35. The change was 35, so I had to start somewhere lower than that. A sample of water is heated from 282 Kelvin to 292 Kelvin by the addition of 3,000 joules of heat. So I need my difference, so 297 minus 282 is going to give me 15 for my delta T. So I've got a delta T equal to 15. This is my Q. They want to know what was the mass. I don't know my mass. So again, I have to rearrange my formula. I've got Q equals MC delta T. I'm trying to solve for mass. This was all multiplied, so I'm going to divide by C delta T on both sides. And I get M is equal to Q divided by C delta T. So where can I squeeze this in? Let's see. Mass is equal to Q, 3,000 joules. I'm not going to put the units in here to save a little space. My C is 4.18, and my delta T is 15. So 3,000 divided by 4.18 times 15 is going to be 47.8 grams. So this equals 47.8 grams, which is really this answer here. And we know it's in grams because they were looking for mass. Okay, moving along. If a 4-gram sample of water, so this is my mass, 4 grams, at 10 degrees, so this is kind of my TI, it's at 10 degrees, absorbs 20 joules of heat. This is my Q. The temperature of the sample would be raised by how many Kelvin? So we're looking for our delta T. We're looking for our delta T. So I'm going to use Q equals MC delta T. I'm solving for delta T, so I divide both sides by MC. So I get delta T is equal to Q divided by MC. And we said our Q was 20, and our M is 4, and our C is 4.18. So 20 divided by 4 times 4.18, and my delta T is equal to 1.2, and that's Kelvin. And it would be Celsius or Kelvin, it doesn't matter because it's 1 degree is 1 degree on both scales. Sorry. Okay, last two problems. How much energy is required to convert 100 grams of water solid to 100 grams of water liquid? So solid to liquid, that is heat of fusion, Q equals mH sub F. So we're using Q equals mH sub F. I have to recognize H sub F as a constant that I get from table B, which is 334 joules per gram. So I've got my mass, which is equal to 100 grams times 334 joules per gram. Grams cancel. 100 times 334 is 33,400 joules. And the last, how much energy is released when 10 grams of water vapor condenses. Condensing is the opposite of vaporization, which is boiling, so I'm going to be using Q equals mH sub V. Now, when water boils, it goes from a liquid to a gas. It's going uphill. That would be an endothermic process. So if I'm going from a gas to a liquid, I'm going downhill. That's an exothermic process. So I just have to remember that when I state my answer. So my heat of vaporization is 2260 joules per gram. So I've got 10 grams times my heat of vaporization constant, 2260 joules per gram. Grams cancel, and I'm left with 22,600 joules released, or you can write it as negative 6,000 joules, which also indicates that it's been released. Okay. That's a lot for review session 1. Again, this is layered material. You're going to see some of this again in other lectures. I hope it was helpful to you. Have a great day.